All right, this is sort of a straightforward application of the fundamental theorem. So let's actually draw out what the diagram looks like, because I think that at least for me, I love drawing out the diagrams. The more visual, the better. It just really sticks in my head, and I really kind of see what's going on. So what we want to do is we got something over something being isomorphic to something. So what that's going to look like is the something over something is going to be this thing in the bottom corner here. And then we're going to want it to map into this thing on the upper corner by this eta bar. This eta bar is going to be the desired isomorphism. And it's kind of given away that you've got something divided by something here being isomorphic. That's what gives away that this eta bar is going to be the desired isomorphism. And so you just kind of fill in the rest of everything of like what it could be. So mn over mni, obviously that means that what we're starting with is mnr, and we're going to want some map whose kernel is mni. And so the natural thing to think of is aij plus I. So basically what this does is you take a11 through a1n, an1 through ann, and you map this matrix to a11 bar, or rather a11 plus I, an1 plus I, a1n plus I, ann plus I. So this is our actual map eta, and this is what we want to prove gives rise to eta bar being in isomorphism. All right, so let's actually do that. So first, we need to show that eta is a homomorphism of rings, right? We'll see. Eta of the matrix, when I do aij here, it's going to be referring to a matrix unless I specifically say otherwise. So I just write this instead of doing eta of the matrix aij, because then you have to have like a lot of parentheses. I don't want to do that. So anyways, eta applied to the matrix aij is 0 if and only if, well, what's the 0 element of mnr slash I? It's got to be 0 at every single thing, so it's got to be 0 plus I, which is just I, because that's the 0 element of R mod I. Right, because that's where modding out. So this holds if and only if aij is in I for all I and j, which holds if and only if aij is in mni, and so the kernel of eta equals mni. So this should kind of give you the idea that this isn't quite the right order to do this in. Like typically you'd first prove that it's a homomorphism, and then you'd prove that it has this kernel. But we kind of want to make sure that this eta that we've chosen is the right eta, because we aren't told in the problem what eta to use. And so the fact that its kernel is precisely what we want to mod out by is a really good indication that we're on the right track. So, by the fundamental theorem on homomorphisms, or what of homomorphisms, whatever it is. So by this, if eta is an epimorphism, then eta bar is an isomorphism. And remember, epimorphism is, I haven't seen this anywhere outside of Jacobson, but it might be standard. It's just a surjective homomorphism. You might remember this if you've never heard of monomorphism or epimorphism like I hadn't before this textbook. You might think like, oh, these are special things. There are more specific types of morphisms or of homomorphisms, and so how more specific could you get? Oh, you could add injectivity or you could add surjectivity. Those are the kind of the natural things that you'd think to add. And so you think, okay, well, one of them so epimorphism is going to be either injectivity or surjectivity. The way I remember it is that monomorphism, like injectivity is also 1-to-1 and mono is 1, so I sort of make that connection. I'm not sure if there's any reason why, if there's any correlation between a function being 1-to-1 and the choice of calling it a monomorphism. I'm guessing it's just a coincidence, but it helps me remember it, so it works. So eta is surjective since the matrix Rij plus I is given any matrix in MNRI, you can write it as Rij plus I because that's what the elements of R mod I look like, and this is just by definition eta of Rij, and Rij is just an element of MNR. So for plus, we want to prove that this is a homomorphism with respect to plus. So eta of 0ij is just, you could write it as 0ij plus I, to emphasize that this is a matrix of elements of the form 0ij plus I, because what I'm going to write next is a little ambiguous. It's just I in parentheses, and you might think, oh, is that just I itself? No, it's not. This I refers to the I in parentheses here refers to the collection of n by n matrices whose elements are in I. No. The collection of n by n matrices whose elements are the set I as an element of R mod I. Okay? So there's that. And of course this is the zero element in Mn R mod I, because it's a matrix that consists entirely of the zero element. And eta of Aij plus Bij, these are both matrices. That's just going to go to Aij. Each entry is going to look like Aij plus Bij plus I, but we can write this as Aij plus I plus Bij plus I. In particular, one of these I's you could just, because any element of the form Aij plus Bij plus I can be written in this form because I plus I equals I. That's the main thing that's going on here. And so this is Aij plus I plus Bij plus I, and that's eta ij. Man, I should continue doing these videos during the day when I have a lot of energy, and not like at night like I always do when I'm really like drowsy and worn out. Anyways, multiplication is defined by matrix Aij plus I times Bij plus I is the matrix consisting of sum from k equals 1 to n of Aik plus I, then Bkj plus I. These are the elements, but this is just k equals 1 to n of the element Aik Bkj. Here, I might put this all in parentheses just to make sure that, well, we've got the sum from k equals 1 to n. That kind of makes it obvious that this thing should be all together. Oh wait, no, but the upcoming I squared, it's not obvious that that's contained in each sum. But anyways, if you move this around, because I is an ideal, you can just kind of combine a bunch of things together. It's AIKBKJ plus I with identity 1 plus I. So eta 1 equals this identity element 1 plus I, and lastly, I don't want to scroll down past the picture, eta of Aij times Bij is eta of the sum k equals 1 to n of AIKBKJ, which is equal to k equals 1 to n AIKBKJ plus I. Oh, but have we seen this before? This is just Aij plus I, Bij plus I, which, as it turns out, is eta Ij, eta Bij. Thus, eta is a ring epimorphism. Then hence, MNR mod MNI is isomorphic to MNR mod I, and the isomorphism is given by eta bar. And there we go. This completes our proof.